Hey folks, today we are going to do part one of graphing rational functions. So today we're going to graph rational functions using a transformational approach, and we're also going to see one other form of rational functions to graph, and we'll investigate and analyze these functions and look at function characteristics. Okay, so let's get started. So when we were doing variation, we looked at inverse variation. So we looked at the function f of x equals 1 over x. So let's revisit this. Let's plug in some values for x. So if I plug in negative 2, I would know I would get negative 1/2. If I plugged in negative 1, I would get negative 1. If I plugged in 1, I would get 1. If I plugged in 2, I would get 1/2. So let's plot these points over here. So negative 2 is at negative 1/2. Negative 1 is at negative 1. 1, 1, 2, 1/2. Okay, and so these points right here, but that doesn't give us a clear picture. So for right now, let's take a look and use the graphing calculator to aid us on what the picture looks like. So I've already put in 1 over x into the y equals, and we can see what the function looks like right here. So I can go back to my graph and I can finish filling it out, and it seems to go like this. Right there. And let's think about that. If I plugged in a positive 1/2, if I plugged in 1/2, I'd have 1 over 1/2, which would be 2, so I know that point would be on there. If I plugged in 3, I would be a third. If I plugged in 5, I'd be a fifth. So it's getting closer and closer to 0. Okay, as I plug in bigger and bigger numbers, our function is approaching 0. In the same way, as I head towards negative infinity, if I plug in smaller and smaller numbers, 1 over negative 2 is negative 1/2, 1 over negative 3 is negative 1/3, negative 1/5, on and on. It's getting closer and closer to 0 that way. Okay, so it's as we go to positive infinity, it's approaching 0. As we go to negative infinity, it's also approaching 0. But what's happening right here in the middle at 0 when x is 0? Well, if I do 1 over 0, that's undefined. Okay, so that value does not exist. But as I approach 0 from the right over here, as I approach it from the right, my values are increasing without bound. They're getting higher and higher towards infinity. So it's as if we are approaching a line right here. We're approaching this pink dotted line. Okay, and the same way we are approaching in the x direction that line. And what are these two lines called? These are called asymptotes right here. Okay, and in general, asymptotes are lines that your function approaches. Okay, so we are approaching two lines. We're approaching the line y equals 0, and we're approaching the line x equals 0. Okay, so for today we're going to talk about two types of asymptotes. Horizontal asymptotes, those describe the end behavior of the graph. What is happening as your graph heads towards positive infinity, and what is happening as your graph heads towards negative infinity. The other type of asymptotes we're talking about are vertical asymptotes. So this line x equals 0 is a vertical asymptote, and that is a line that your function approaches and grows without bounds. So vertical asymptotes describe where the graph grows without bounds, where it heads to positive infinity and where it heads to negative infinity in the y direction. So we could write on this, we could write that our horizontal asymptote, that is at y equals 0. And our vertical asymptote, that is at the line x equals 0. It's always equations of lines to describe asymptotes, okay? And so at 0, we need to go back to that. At 0, our function was undefined. And vertical asymptotes are going to occur where your function is undefined. Okay, sometimes, and we'll get to this later on, you can have other types of discontinuities. So let's take a look at this one right here. I have 1 over x minus 3 plus 1. So I'm going to graph that, and we'll take a look at that. All right, so here I have it entered in the calculator. You can see how I entered it in. I put the denominator in parentheses because you need to do that. If I graph it, it looks like this. So it's the same general shape, it's just shifted. Our graph is shifted. And where does it look like our vertical asymptote is now? It looks like our vertical asymptote is right here at the line x equals 3. So I can put that right here. The line x equals 3. And where is our vertical asymptote? Well, our vertical asymptote seems to be right here, and that's at y is equal to 1. Right there. Well, how does that relate to our graph right here? So, well, we have a horizontal asymptote at y is equal to 1, and we have a vertical asymptote at the line x is equal to 3. Okay. Well, where did these values come from? Well, they just come from right here. Our vertical asymptote is whatever makes our denominator equal to 0, because that's when we would be dividing by 0. So that's at 3. And then this value over here, that raised our graph up one value. So instead of having a horizontal asymptote at 0, it raised it up to 1. And so this is our transformational form of our graph, where we have y is equal to a over x minus h plus k. Okay, and we've done this transformational approach in all of our functions so far. So in this case, this is our horizontal movement of our vertical asymptote, and this is our vertical movement of our horizontal asymptote. So how can we plot points on this? Well, if we look back at our regular one, our normal, we go over 1 and we would go up 1. But I have a value of 1 here, so it's still going to be over 1 and up 1 for that point, and then over 1 and down 1 here. Okay, so it's going to follow the exact same pattern. When we were at half, it would have been at 2. When we were at 2, it would have been at half right there. The same thing on this side. It's going to follow the same pattern, and I can graph it right here. And then just plug in, fill in the rest. Okay, so let's talk about some function characteristics for this. So we already have our asymptotes at y equals 1, our verticals at x equals 3. So our domain on this, okay, what can x not equal? Well, x cannot equal wherever our vertical asymptote is, because if we plug that in, we'd be dividing by 0. So x cannot equal 3. What about our range on this one? What can y not equal? Well, y is never going to approach the value of 1. So y will never eat the value of 1. How about our end behavior? We can write our end behavior. Okay. As x goes to infinity, f of x is headed where? Well, as x heads to infinity, our graph is approaching this horizontal asymptote of 1. And as x goes to negative infinity, f of x is approaching our horizontal asymptote of 1 just from the opposite side. And let's think about why that is. As we plug in a larger and larger number for x, that means this fraction is getting smaller and smaller and smaller. It's approaching 0. As our denominator gets bigger, we get 1 divided by a larger and larger number. So this is approaching 0, and then we add 1. So it's going to be slowly approaching a value of 1. Now, how can I find my intercepts for this graph? if I want to find the y-intercept of this graph, I would just plug in 0 in for x, because our y-intercept occurs right here when we plug 0 in for x, when our x value is 0. So if I do that, I can find our y-intercept. We have y is equal to 1 over 0 minus 3 plus 1. Well, this is just a negative 1/3 plus 1. Negative 1/3 plus 1 is 2/3. So our y-intercept is at the point 0, 2/3, as we can see right there. Now, let's find our x-intercept. To find our x-intercept, we want to plug 0 in for y into our function. So if I do that, I have 0 is equal to 1 over x minus 3 plus 1. Now I have a rational equation I need to solve. So I can move the negative 1 over. So I have negative 1 is equal to 1 over x minus 3. Well, our LCD is x minus 3. So if I multiply both sides by x minus 3, if I do that, those cancel, and I have 1 is equal to, well, negative 1 times x minus 3 would be negative x plus 3. And then if I move this over, I would have x is equal to negative x, excuse me, is equal to negative 2. So therefore, x would equal 2. So our x-intercept, and it's one of the points we actually plotted, is right here at 2, 0. So at the point 2, 0. So I can write that here, 2, 0. Okay, that is our x-intercept for this graph. All right, let's take a look at this graph, and let's try to not use a calculator for it. So based on what we've talked about in this one, our horizontal asymptote, okay, that is right here. That's at y is equal to 2, because this is going to get closer and closer to 0 as x gets bigger. So our horizontal asymptote is at y equals 2. So I can put that in. Our vertical asymptote is, well, what's going to make our denominator equal to 0? Well, that's negative 5. So our vertical asymptote is at x equals negative 5. Okay. And now let's look at our dilation. Our dilation is negative 3. So instead of from here where they cross, of going over 1 and up 1, I'm going to go over 1 and down 3. Instead of going to the left one and up, or left one and down 1, I'm going to go to left 1 and up 3. So I know those 2 points are on my graph. Well, how can I figure out some other points on my graph? One way to do it is to plug in values for x into your function. So suppose I want to know what the value is right here at negative 2. I would find f of negative 2. So I would just plug in negative 2 in for x. So here I've plugged negative 2 in for x, and I got a y value of 1. So I have these 2 points right here. Now, anytime we are in this transformational form, our rational function is going to have the same general shape. Now, our arcs might be on different sides depending on what our dilation is, but they're going to always have the same general shape. So I know if I have these 2 points, my graph is going to go like this, because our graph always approaches our asymptotes as we head towards infinity in either the x direction or the y direction. We're going to approach our asymptotes. So that's what it looks like on this side. Well, how about on the left side of the vertical asymptote? Well, I could plug in another value. I have negative 1, negative 2, negative 3. 8. I can plug in negative 8 over here just to get see how soon it swoops down. So I'm going to plug in negative 8, and let's see what that is. So if I plug in negative 8, you can see the work right here. I got a value of 3. So, and it's symmetric. Notice how these mirror each other. And so if I graph this, I have that one right there. Okay, so we can figure out our function characteristics on here for this one. Our domain for in transformational mode, that x cannot equal whatever our vertical asymptote is, which is -5. Our range, when our rational function is in transformational form, is that y such that y will not equal value of 2. Our end behavior, we can write it out. Well, as x approaches infinity, f of x goes to 2, and as x approaches negative infinity, f of x also approaches 2. It approaches our horizontal asymptote because that's what that describes, where we're headed as we go to infinity. So what I want you guys to do right now, pause the video, try to solve for the intercepts, x and y intercept, come back and check your answers. Okay, hopefully for the y-intercept you got 7/5, which is a bit over 1, as we can see on the graph, it matches. And for your x-intercept over here, after plugging 0 in for y and solving it like the previous one, I got -7/2, which is -3.5. And see, that's right about where that crosses. So that is good. So that's how you can graph a function in transformational form. Generalize what A, H, and K do to our graph. Now, it's the exact same thing that they have always done. A is our dilation. H is our horizontal shift. And this horizontal shift acts on our vertical asymptote. And then K is our vertical shift. And what that does is raise and lowers our horizontal asymptote. So what about when our graph is in this form? Okay, it's not in transformational form. I have y is equal to 4x plus 1 over 2x minus 3. Well, let me graph this and we can take a look and see if we can figure anything out from the graph. So this is how I entered it into the calculator, numerator, denominator, both in parentheses. So let's take a look at what we have. So it looks like this. It's the same general shape, which is nice, of the parent function of 1 over x. And we can see it has been shifted, but how much and where at. So let's see. Our vertical asymptote, where it's headed towards negative infinity and positive infinity in the y direction, well, that seems to be right around here. Not quite at 2, because that kind of hits it, but and not at 1. So kind of like right in between at 1.5. Okay, it looks to be at 1.5 for our vertical asymptote. So vertical asymptote seems to be at x equals 1.5, or 3/2. And what about our horizontal asymptote? Let's see if we can get an idea of where that is. Well, it's going up here. It's going down here. It's somewhere in between. So it looks to be around 2 is where our horizontal asymptote is. So it seems to be at y is equal to 2. And where might that be from our function that we have, our function? Well, let's look at our vertical asymptote. So previously, our vertical asymptote was where the denominator of our fraction was 0. And that's the same thing here. Whatever makes our denominator equal to 0 at this point, okay, that's where our function is undefined. And where is this equal to 0? If I set that equal to 0, I will get x is equal to 3/2. So that is indeed our vertical asymptote. So I can plot that on here. And what about our horizontal asymptote? Well, that's a little trickier. Okay. Well, let's think about this function as x is getting really, really big. As x is getting really, really big, adding 1 and subtracting 3 from our values, is not going to affect our fraction that much. Because if x is 1 billion, 1 billion and 1 is not going to be that different from a billion itself. The same way, taking away 3 is not going to affect the value as much. So as I get really, really big, this +1 and this -3 don't really impact the graph that much. So you can imagine if they're not impacting the graph that much, these are sort of going away as x gets really, really big. Okay, so as x gets really, really big, I'm having 4x over 2x. So as x gets really, really big, 4x over 2, 4 over 2 is just 2. And that is how we get our horizontal asymptotes. We have to look at the coefficients of our two leading terms of our highest degree. 4 over 2 is 2. So that is going to be our horizontal asymptote right there. All right, so let's write our domain and range. Well, our domain, before we finish graphing, our domain on this is that x, such that x cannot equal 3/2 still. Range, we still find the same way. It's at our vertical asymptote. Excuse me, our range is at our horizontal asymptote, equals 2. And what about our x and y intercepts for this? Well, our y-intercept is when we plug in 0 in for x. So if I plug in 0 in for x, what's happening right here? Our y-intercept, if I plug in 0 in for x, I would have 0 times 4 plus 1 over 2 times 0. Well, that's just 1 over -3, which is -1/3. If I plug in 0 for x, all my x terms go away, and I'm just left with -1/3. So our y-intercept is at 0, -1/3. How about our x-intercept? Well, since this is one fraction, when is this going to be equal to 0? If I want to plug in 0 in for I, when is this going to be 0? Well, it's going to be 0 only when our top is 0, because 0 divided by anything except 0 itself is going to be 0. So to find our x-intercept, all you have to do is set the top equal to 0 when it looks like this. So our x-intercept, if I set the top equal to 0, I would have 0 is equal to 4x, our numerator, sorry. If I solve this, I would have x is equal to -1/4. So our x-intercept is at -1/4. So it's at -1/4, 0. So it's right there. So this is at -1/4. And then our y-intercept again was at 0, -1/3. Okay. And so we have these two. So we know that one of our arcs is going to be on this side. And so the other one has to be over here, but I want a point. So whenever we're looking for points, what we need to do is we need to plug in values for x. So we need to evaluate our function at different points. So the first one I'm going to do is I'm going to evaluate my function at, let's see, 1, 2, 3, 4, 5. Let's evaluate the function at 5 and take a look at what we have here. So let's do f of 5 and figure out what we have. So I'm going to plug in 5 into this. So I have 4 times 5 plus 1. So this is 21 over 7. So this is 3. So at 5, we have a value of 3. So 1, 2, 3, 4, 5 have a value of 3. So we know it's here. Let's get something a little closer. So let's do f of 3. Okay, so we want a little closer to our asymptote to figure out a nice value. So if we do that, it's 4 times 3 plus 1 over, and that's going to be 13 over 6 over 3. Okay, so 13 over 3. So that's a little bit over 4. Okay, it's a little bit over 4. So if I plug that in, 1, 2, 3, 4, a little bit over 4, 4 and a third, it's right there. So I know that I can graph my function now. I know its general behavior. So it's headed up like this because it approaches our vertical and it approaches our horizontal. Now, if you want more points, you can always evaluate your function at more points to get a better picture of what it's going to look like. There is no maximum amount of points that you can use. You can always evaluate more if you want to get a better picture. And I know it's going to approach like this through these two, and it's going to head down like that through there. So that is the information for this particular graph. So let's generalize a bit. If I want to find the asymptotes when it looks in this form, I have ax plus b over cx plus d. To find our horizontal asymptote that is at looking at the coefficient. So that is at the line y is equal to a over c. And our vertical asymptotes, that is when the denominator is equal to 0. So we set denominator to 0 and solve. And that'll give us our vertical asymptote. Alright, so let's take a look at one more, and I'll leave the last one for you guys to try on your own. We'll check it in class. So I have 5x minus 1 over 2x minus 6, and I want to figure out some information about this. So the first thing, if I want to find the horizontal asymptote, I need to look at my coefficients of my linear terms, my x terms. It's 5 over 2. So I know that the horizontal asymptote is going to be at y is equal to 5 over 2. So I can put that in as a dashed line, 5 over 2. My vertical asymptote is whenever the denominator is equal to 0. Well, when is that going to be equal to 0? That'll be equal to 0 when x is equal to 3. You could always solve it if you needed to. And then I would have 2x is equal to 6 and x equals 3. So that is our vertical asymptote. That's going to be at x is equal to 3. Right there. Okay, so I can complete my domain and range. Let me write those up. So my domain is that x cannot equal 3, and my range is that y cannot equal 5 halves. If I want to figure out my intercepts, my y-intercept, I just plug 0 in for x. If I plug 0 in for x, up here these two parts go away, and I have negative 1 over negative 6, which is just 1/6. So the y-intercept is at 0, 1 over 6. If I want to find the x-intercept, you just set the top equal to 0. If I set the numerator equal to 0 and I solve that, I would get 1/5. So I set the numerator equal to 0 and I get 1/5. Again, if you wanted to, you could write it out. And I would have 5x is equal to 1 and x is equal to 1/5. So that is my x-intercept. So I can plot these. So I have 1/5, 0. It's that little fellow right there. 0, 1, 6. It's the best approximation right there. They're hugging each other right there. But I don't have a lot of other information about this. So what I need to do is I need to plot some more points. So let's figure out what's happening at 1. And you might be thinking, why am I picking these specific values? Well, I don't really have a whole lot of ones in mind. What I'm doing is I'm just picking values that are spaced out in this range, some that are getting closer to the asymptote, just so I can get a general idea right here. So I'll probably pick one right around here, maybe one over here to pick the value. But you don't have to pick the exact same ones that I do when you're doing this. You can pick whichever ones you want. So I'm going to find f of 1 for this. F of 1, if I do that, I have 5 minus 1 over 2 minus 6. So this is 4 over negative 4. So that's negative 1. So f of 1 is at negative 1. So now I know it's dropping towards my vertical asymptote there, and it's gaining towards the horizontal. So that's probably good for this side over here. But I don't have anything on the right side of my asymptote, because you always have to check both sides of the asymptote. So let's check over here. Let's get some pictures. So I'm going to find, well, 1, 2, 3, 4, 5. Let's find f of 5. If I do that, so I would have 5 times 5 is 25 minus 1 over 10 minus 6. So it's 24 over 4. So this is 6. So at f of 5, I'm going to be at 6. Okay, so it's right there, and I need at least one more on that side. So let's find f of 7 on this side. So over here, figure out how quickly we're dropping towards our horizontal asymptote. So if I plug in 7, I have 35 minus 1 over 14 minus 6. If I do that, what am I getting? I'm getting 34 over 8, which is 17 over 4. 17 over 4 is just a bit over 4, because 16 over 4 is 4. So 17 over 4, 1, 2, 3, 4, a bit over right there. So that gives me an idea. So now for myself, I have a good picture of what this is going to look like. Dropping down, heading towards up that way, and then dropping down that way. So that is a good picture for me. Okay. All right, I leave this last one to you guys. Try to do this. We will go over it after we take the entrance quiz in class. Have a good day.